Okay, so this is a chi-squared test for goodness of fit. This is not chi, it's chi. The Greek letter for chi is this cool little X. He's kind of wavy and long on the bottom right, and then just a stick coming across the other side. But it's always capital. So that's chi-squared test for goodness of fit. Okay, now notice, these are inferences for distributions of what kind of data? Tell me about categorical data. It's who? What? It's in buckets. So it's some sort of adjective. Blondes, brunettes, redheads, red cars, black cars, white cars, juniors, seniors, freshmen, sophomores. So something that's used to describe. Not something you measure, not miles per gallon. Okay? Okay. And this problem is about chocolate. Bless you. Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. Do you have a favorite color of M&M? Y'all don't care? You don't care? Y'all are the first class to ever say that. Most classes are like, oh my gosh, I love the green ones. They don't taste any different. Y'all understand that, right? They don't taste any different. And then there was a movie that said, what was the name of the movie? It has Jennifer, it has J-Lo in it. Yeah, it says you can only eat the brown ones because the other ones, because chocolate's already brown. And the other ones have more artificial flavor. I'm pretty sure that's a lie. I mean, I know chocolate's already brown, but I'm pretty sure that shell has artificial flavoring in it. Anyway, okay, so the M&M's Corporation, Mars Corporation, says it will contain 13% brown, 13% red, 14% yellow, 16% green, 20% orange, and 24% blue in every bag. We want to know if their claim is believable. So we should look at the difference between the observed values and the predicted values in each category. So here I go. I've got a bag of M&Ms, and I'm going to count all the different colors. So I do like a tally. Now, are these numbers in this chart observed or predicted? They are observed. They are what I saw with my eyeballs. They are what actually happened. Okay? We could use a one-sample z-test for proportions to test each individual proportion. So guys, I could do a z-test for proportion to see if the blues are right. And then I could do a whole nother z-test for proportions to see if oranges are right. Anybody want to do that? Okay, so what we're going to do, what a chi-squared test does, is to see if the claimed distribution from Mars fits what we actually got. But not only would this test be inefficient, we would be doing multiple comparisons. More importantly, this approach wouldn't tell us how likely it is to get a sample of 60 candies with a color distribution that differs from the one claimed by the company. For that, we need a new kind of significance test, and it's called a chi-squared test for goodness of fit. Goodness of fit. How well does what happened fit what they claimed should happen? Chi-squared tests for goodness of fit are only used for categorical data, like the color of an M&M. As with any test, we start with a null and an alternate. Now notice, there are no numbers in my null and my alternate. They are sentences. That's new. My null is that it fits. My null says the company stated color distribution for all M&Ms is correct. It fits. It's true. The alternate is going to be that it's not true. That's it. There's no greater than, there's no less than. It's just that it doesn't fit. The idea of a chi-squared test for goodness of fit is this. We're going to compare the observed counts, what we saw with our eyeballs, from our sample with the counts that would have been expected if H sub O is true. The more observed counts differ from the expected counts, the more evidence we have against the null hypothesis. That's a powerful sentence. I'm going to say that again. I'm right here. The more the observed counts are different from the expected counts, the more evidence we have against the null hypothesis. And what was the null hypothesis? That it fits, that it's true. So the more these are different, the more evidence we have to say, no, they're not. We reject it. Okay, so tell me, observed, how many blues did we actually have? We had 9. How many oranges? And greens? And yellows? And reds? And browns. Okay. Now, how many should we have expected? How do you find that? Because they gave me percentages. I got to take it from my total. How many total M&Ms did we have? 60. So they said how much should be blue? What percent? 24% should be blue. So I need to do 60 times 0.24. What we got? No, I would go with decimal. And if it's 14.4, I wouldn't go up to 15 anyway if I was going to round. It would stay 14. Oh, no. I would go with decimal. I understand what you're saying. It's a thing for each problem. Okay, the orange was 20%. And the green was 16%. And the yellow was 14%. And the red was 13%. And the brown was 13%. Okay, everybody good? So tell me what information I have. I have my observed, and I have my... Now, to the untrained eye, someone would look at this and say, yeah, they're pretty different. I think it's bad. They're not asking your opinion. They're asking you to prove it. So we're going to prove it with a chi-square test. Grab your formula sheet, flip to the back, and look at the very bottom, which is very appropriate because this is our last chapter. But it's kind of in order, yeah. All right, y'all see it? That is chi-squared. You don't ever have to memorize that. Ever, ever, ever. You just got to be able to use it. Okay? So, this is chi-squared. What is this symbol right here? It is the sum. That is sigma, and it means sum. So, I'm going to sum observed minus expected squared divided by expected. But I have to do that for each color of M&Ms, and I have to add as I go. Do you understand that? So like I would do, if I was going to do this by hand, which I'm not, I would do 9 minus 14.4 squared divided by 14.4. And I would get that answer. And whatever that answer is, and then plus, and then I would go do it for oranges. And then I would go do it again for green. And I'm adding as I go. Do you understand what that means? Okay, watch. Grab your calculators. Go to Stat. Edit. Type your observed very carefully into your L1. and then go type your expected into your L2. And then give it a once over to make sure you typed everything incorrectly. All right, I think I'm good. Y'all good? Okay, now I want to go to L3. And I want to tell it to do this part. Notice that I did not highlight the sigma, okay? Just observed minus expected squared over expected. So who, let's see, parentheses. Who is my observed? Okay, so L1 minus L2, now what? Whoa, parentheses, squared, divided by L2. Boom. Okay. Now, you're not done. The formula says I want to sum them. Now, I don't want to write all these down and then add them all together on my calculator. What can you do that produces a screen of information where sigma is on it? One variable stats. But guys, I need to one variable stats my L3. It's not an E. It's not an E. No. E is another number. Very good. It's just this guy. Because it doesn't say to sum the whole thing squared. I've already got that squared in my formula. Chi-squared is the sum of this thing. So, what's my chi-squared? 10.180. You have to go 3 decimal places. You have to be correct to 3 decimal places. Now, if you wanted to, you could do 10.1799 if the double nines freaked you out. But that fourth 9 is telling my third 9 to round up. So it takes the 79 up to an 80. So my chi-squared is a 10.180. Okay, now let's talk about what this means. I want you to think of chi-squared as a measure of the distance of the observed counts from the expected counts. Like any distance, it is either 0 or positive. Will you ever get a chi-squared that's negative? No. Right, it's a distance, and that's why the formula has it squared. Larger values of chi-squared are stronger evidence for H sub A. Who is H sub A? Your alternate that it doesn't fit. So the bigger your chi-squared, the more evidence you have that this is crap. But the smaller chi-squared suggests that H sub O is good, that it does follow, that it's consistent with what they claim. So how do we know if it's big enough? Well, we're going to find its p-value, and we're going to compare it to the level of significance for this test. But, guys, we are not a normal distribution. We are not a t-distribution. We are a chi-squared distribution. This is your last distribution you got to learn about. This is what it looks like. Now, y'all just said chi-squared will always be positive, correct? So guys, when you draw this, do you see how it has a backbone? When you draw this, that's how you draw your chi-squared. He is peaked at the beginning and then tails off. That's chi-squared. Now, what happens, what's causing it to spread out like that? Do y'all see that? Degrees of freedom. Now, what are the degrees of freedom based on? Sample size minus 1. So can you make a conclusion about the sample size and what your chi-squared looks like? The bigger your sample size is, the more spread out your chi-squared is. The more what? The more normal it looks. Do y'all see that? Doesn't this almost kind of maybe look normal-ish? But you guys know that a normal curve is not all positive, right? A normal curve sits right there at 0. So this is not a normal curve, but it has a more of a normal shape to it, the higher your degrees of freedom get. I don't ever draw, like when I'm finding my p-value and I do my little graph, I always draw it like this. Always. I don't adjust it based on my degrees of freedom. Okay? Notice that it only takes on non-negative values and is skewed to the right. It is not symmetrical. It depends on its degrees of freedom, which is the number of categories. Okay, now hold on. Not the number of M&Ms. The number of categories. How many categories did you have? 6. So what's your degrees of freedom? 5. Okay, so how many categories of M&Ms do we have? 6, so our degrees of freedom is, so be careful there. It's not number of M&Ms, it's number of categories. As degrees of freedom increase, the graph becomes more bell-shaped and looks more symmetrical, and to the untrained eye, it looks more normal, although you know it's not. Notice that the mode, the high point, occurs over n minus 2. Now this I added after I saw some release problems that asked a multiple choice question about the peak of a chi-squared distribution and where it happens. So it happens over n minus 2. The p-value, what's n by the way? Sorry. So look here, if my degrees of freedom is a 3, what were my categories? 4. So where should it peak? It's 4 minus 2. So do you see how it's kind of sort of maybe over 2? It peaks over n minus 2. The p-value is the probability of getting a value of chi-squared as large or larger. Therefore, I hereby declare that all chi-squared tests are right-tailed. Remember, your alternate hypothesis, there's no greater than, less than, there's none of that. Chi-squared tests will always be right-tailed. So to find your chi-squared p-value, you are going to chi-squared CDF from low, which is going to be your chi-squared number, to high, which is infinity, and then your degrees of freedom. Correct. Use the M&M's data to find its p-value and make a conclusion about the sample distribution of Miss Patterson's M&M's. All right, what was my chi-squared 10 something? 180. Okay, so I'm going to draw. And when I draw this distribution, guys, draw it with a backbone. Because you are communicating to them that you know that this sucker will always be positive. So draw it with a backbone. Always. Now look, some of you are forgetting your degrees of freedom formula on your test. That cost you a point. That hurts. Degrees of freedom is not I mean, I guess you could still write n minus 1, but just remember it's number of categories minus 1. I would. Again, communication. You are communicating to the powers that be that you know that it's categories. Even though you put a 6 there and it's pretty obvious, we are still communicating. Okay, so now go to your calculator where all your CDFs are and see if you can find the chi-squared CDF. Number 8, we concur. Okay. Anybody got a number? What comes after the 9? A 2? 2, 9, so that should be a 3. That is your p-value. And notice I did not just write 10.18. I anchored it with a chi-squared because you don't ever have like floating numbers. Okay, now it says use the M&M data to find its p-value and make a conclusion. Well, there sits my p-value. What's your conclusion? Did it tell me what my level of significance was? Okay, so first we have to assume that my level of significance, assuming a level of significance of 0.05, can we just talk it first? Assuming my level of significance is 0.05, my p-value is greater than the level of significance for this test. Therefore, we fail to reject H sub O, concluding what are we concluding?
The company's stated color distribution for all M&Ms is correct.
Perfect. If we fail to reject him, that means we are accepting him. That means we are concluding there is enough evidence to conclude that the company's stated color distribution for all their M&Ms is correct. Period. Our data is not statistically significant. Okay, now you try. You write. There is not enough evidence to conclude, hold on a second. We said our evidence statement based on H sub O, and we should say our evidence statement based on H sub A. So if we're sticking with H sub O, then we say there is not enough convincing evidence to conclude. Right. I'm just going to put whatever your H sub A is. And you literally just go back and restate that. All right. Just to clarify, to make sure we're driving this point home, we only use a chi-squared test for goodness of fit when you have categorical data describing one variable. Now look, I'm emphasizing this because we have 2 more chi-squared tests coming. And they are different than that sentence right there. So this is how you know it's a chi-squared test for goodness of fit. It has to be what kind of data? Categorical, and how many variables? 1. What's our variable for the M&Ms? Color. That's your variable. You can use the numbers to think of like a percent or a proportion. So nothing you would find an average of, but a proportion or percent. Hair color distribution in a school, number of students in each AP class, types of trees in a forest. No averages, no lengths, nothing quantitative. Must be categorical. Think of proportions and percents. All right. Conditions. Same old, almost. It still has to be random. It still has to be independent. LCC. It's not NP and NQ. It's all your expected counts have to be bigger than 5 or higher. So not 10. Who are my expected counts? Your second column, your L2s, not your observed, your expected. Okay, so let's check the conditions for M&Ms. Are we random? Let's go back and read. Just look at the difference she observed. Miss Patterson counted the difference of M&Ms in her bag. Table. On average, M&Ms will contain... I don't see anything that says specifically random. Oh, here it is. More importantly, this approach wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs from the one claimed by the company. It is random. It's not super obviously stated in this problem. It will be in the next one, so just hang tight, okay? This one wasn't set up perfectly. All right, independent. I'm still little n less than or equal to 1/10 big N. Now you have to be careful here, because when you think degrees of freedom, what have you switched your brain to now? Categories. But little n is still little n. And how many M&Ms do we have? 60. So here it's still the 60. It's not number of categories. Because that wouldn't make sense, would it? How many? What do we have? 5 categories? 6 categories? 6 categories is less than or equal to 1/10 of all categories of colors of M&Ms. Do y'all see how that doesn't make sense? So 60, 1/10 of what? All M&Ms. Which means I have to have at least how many? I heard it. 600. Now, to be normal, your LCC, you are going to write all expected counts greater than or equal to 5. And then all of our expected counts are sitting where? In that chart. Are they all expected counts? Are they all bigger than a 5? Okay, I am not going to rewrite those. I am going to write this. See chart. You have 15 minutes per FRQ. You don't have time to sit there and write every single expected count. They will either give you a chart, or from the beginning you're going to need to make a chart. A lot of times they'll give you a chart, but it will just have, it'll just be this. And so then I'll write observed and expected, and I'll just come down here and write my numbers underneath to pair them up. So, everybody see how the LCC changed? No NPs and NQs. It's all expected counts greater than or equal to 5, and then I just write C chart. Okay, we're going to do one top to bottom. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it into the highest level of the game. Specifically, because January 1st is the cutoff date for youth leagues in Canada, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. Have you known people who were held back so that they would be the oldest in their grade, so that they would be stronger, bigger, more coordinated, more experienced, and in parents' minds get a better look from colleges? I know several. To see if birth dates is related to success, judged by whether a person makes it into the NFL, that deems a success. A random sample of 80 National Hockey League players from a recent season was selected, and their birth dates were recorded. It is a one-way table, which means it's one variable. Summarize the data on birthdays for these 80 players. Do you agree this is categorical data? Like these could be tally marks. Okay, that's how you know it's categorical data. Now, do you see more birth dates at the beginning part of the year? So what does that mean? 32 what? What kind of players? NHL, National Hockey League, professional hockey players, birth dates are January through March. So they would have been older in their group growing up. Do y'all understand what this is saying? Okay. Does this data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? That's what we're trying to prove. Okay, so what are we? Perfect. We are a chi-squared test for goodness of fit. Okay, would you like one little piece of good news? There are no parameters to define. I don't have an X bar. I don't have a P hat. I don't have a P. I got no variables. I would put the X squared. I mean, technically it doesn't matter. Okay. What is your H sub O? Think about it. So then you would assume that they are not uniformly distributed? Are. Your H sub O is that it's even. It's not like the M&Ms where I gave you specific percentages. I need my H sub O is that all the birthdays are uniformly distributed. What's your H sub A? That they're not. And that's what we're trying to build evidence to say that they're not. So that's going to be my H sub A. All right, the birthdays of who? What's the word you're missing? All, thank you. All NHL players. What? Are uniformly distributed throughout. Now, throughout the year, do I have yearly data? How's my year been broken up? Throughout all the months? I have all the months data? I don't have January data. I don't have February data. I don't have March data. I have January through March data. Ooh, you're close. Quadrants. Divide something into 4. What do you call it? Quarters. Throughout. But no. See, right, but the season is not January to March. I'm pretty sure winter starts before Christmas. I mean, I don't know when the seasons start, but this is not 4 seasons. Throughout the 4 quarters of the year. So if they don't give you percentages to match, then your null is always that it's uniformly distributed. It's all even Steven. So what's your H sub A? Yes, the not of that. The birthdays of all NHL players are not uniformly distributed throughout the 4 quarters of the year. I'm just going to write not. But y'all know for a test or a quiz or the AP exam, you got to write the whole shebang. What do I need to state that hasn't been stated yet? Was it predetermined for me? No, so it defaults to 0.05. No, don't have to, but it is. But it's the only option for a chi-square test. Okay, so that's all the fluffy stuff at the beginning. What's next? Conditions, good. Let's see if we can find random up here. Oh, looky there. Shazam. Random sample. I'm also going to write n equals 80 because I need that for later. Okay, random independent. One-tenth of, what was my 80? NHL players. So all NHL players who have birthdays, but I think that's redundant. But it's not all hockey players, because these are specifically NHL players. Norm. Okay, I am LCC. But LCC for chi-squared. All expected counts greater than or equal to 5. Do I have expected counts yet? Always 5. Each individual expects. I don't know. But does everybody agree we don't have them yet? Okay, so let's go get them. That's your cue right there. Oh yeah, I got to go find those. So go up here and look at this table. Who are these values that are already here? So they are observed. To get expected. Okay, now, how are you getting 20? Okay, so I have 80 players and I have how many categories? 4. So if they are to be evenly distributed, I take my number of sample size and I divide it by my categories, and that's going to put 20 in each one. It's not like the M&Ms. The M&Ms, they gave me specific percentages. I could find the specific amounts. This, my H sub O, is that they're evenly distributed. So now can I put a check mark here? Okay, conditions, done. What's next? As soon as you finish with your conditions, where do you always go next? To your formula sheet. Nope. Chi-squared equals, all right, give me words. Sigma. Now, normally we do words, letters, numbers. Are there letters? There are no letters. So you go straight from words to plugging this into your calculator. Okay, but hold on, time out. The AP graders are very clear on they don't want you to go straight from a formula to an answer. They want to see where the math came from. So here's where you have to throw them a bone. So every time you do this, you have to give them, like, you know, this is something plus something plus something, right? Give them a couple. So what would the first one be? What's observed? What did you see with your eyeballs? 32 minus 20 squared over 20. Give me the next one. Okay, and I know there are only 4, so this doesn't really make sense, but usually I do 2 at the beginning, and then a dot, 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 and then I do the last one. So on this one, that really means we're only skipping 1. What's the last one? So you have to show that. You have to throw them that nugget so that they know that you're not just blindly depending on your calculator, that you know what your calculator is doing. You are communicating to them that you know what it's doing. Okay, now, then I go to my calculator, my sweet, sweet little calculator. I clear all that out, and then I start typing. Why does it make sense that my second entry for my L3 is a 0? 20 minus 20, right? So there's no difference. Okay, great. So what do I do with all those little numbers? So stat, calc, one variable on my L3, which is there from last time. And who do I want? Do I want the sum of x or the sum of x squared? The sum of x. Chi-squared equals the sum of what you just typed in. So a very nice and tidy 11.2. Chi-squared does not have any units of measurement. Now what do I do with my 11.2? I go get a p-value. And how do you draw this? How else do I draw this? With a backbone. I am communicating to anyone who happens to look at my graph that I know how a chi-squared test or how a chi-squared distribution is different from any other distribution. And chi-squared test will always be and right-tailed. So I chi-squared CDF from there to infinity. Oh, what am I going to write now? Degrees of freedom. Now that's not 80 minus 1. Well, 4 minus 1 because it's number of categories minus 1. And again, I'm going to write that because I'm communicating that I know that. And then we go type. Include the zeros. Right. So that's why I went 4. I don't mind that 0 because he's nestled in between two good numbers, but I'm not crazy about him, so that's why I went 4 decimal places. Now, guys, I would take a point off for this. Why? Right, I can't have a floating number. That is my p-value. Okay, just talk to me. Tell me about your p-value. It is. It's very small. It's less than our level of significance. So if it's less than, we are going to reject H sub O and say that there is enough convincing evidence to state this and our data is statistically significant. Right. You're right. I'm going to type.